The solar system contained more than 290 confirmed natural satellites orbiting the planets and dwarf planets, a number that had grown dramatically in recent decades as telescopes became powerful enough to detect the small, dark, distant moons orbiting the outer planets that had been invisible to earlier generations of instruments. Here is every type of moon in our solar system, explained in full. Let's break this down. Regular moon. Regular moons were the natural satellites that had formed in the most orderly and most theoretically straightforward way available to the solar system's formation processes, accumulating from the same disk of gas and dust that had surrounded their parent planet during its own formation in the protoplanetary disk around the young sun, the process of moon formation from a circumplanetary disk being directly analogous to the process of planet formation from the solar protoplanetary disk itself. Regular moons were natural satellites that orbited close to their planet in nearly circular, prograde orbits aligned with the planet's equator, the prograde direction meaning they orbited in the same direction as the planet's rotation, the equatorial alignment reflecting their origin in a disk whose material was distributed in the planet's equatorial plane, and the nearly circular orbit resulting from the dissipative processes within the circumplanetary disk that had damped out any initial orbital eccentricity during the moon's accretionary phase. Regular moons were thought to have formed from the same disk of gas and dust that surrounded the planet during its formation, known as the circumplanetary disk. This process was similar to how planets formed around stars, with the circumplanetary disk being a smaller scale version of the protoplanetary disk, whose physics were governed by the same gravitational collapse, angular momentum conservation, and accretionary aggregation that had produced the planets from the solar disk. Regular moons were typically larger and more spherical than irregular moons, the larger mass accumulated during formation allowing gravity to pull the moon's material into the spherical shape that gravity favored, while smaller moons that had not accumulated sufficient mass lacked the self-gravity needed to overcome the material strength of the rock and ice composing them and remained irregular in shape. The Galilean moons of Jupiter, Io, Europa, Ganymede, and Callisto were the most famous examples of regular moons in the solar system. The four large moons discovered by Galileo Galilei in 1610, whose discovery provided the first observational evidence that not all celestial objects orbited the Earth, and that contributed directly to the acceptance of the Copernican heliocentric model of the solar system. Galileo's observation of the four moons orbiting Jupiter over several nights in January 1610 showed him objects that moved from night to night relative to Jupiter, objects that were clearly orbiting Jupiter rather than Earth, a direct observational refutation of the Aristotelian principle that all celestial objects orbited Earth as the center of the universe. Saturn's large regular moons, Titan, Rhea, Dione, Tethys, and Mimas, were the next most studied collection of regular satellites in the solar system. The Cassini spacecraft's 13-year mission in the Saturn system between 2004 and 2017, having provided the most comprehensive characterization of a regular moon system outside the Galilean system, revealing the extraordinary diversity of geology, composition, and internal structure that the regular moon category encompassed. Irregular captured moon. Irregular moons were natural satellites whose orbits communicated immediately and unambiguously that they had not formed in place around their parent planet, but had instead been captured from elsewhere. Their wide, eccentric, and inclined orbits being the gravitational fingerprint of objects that had approached the planet from heliocentric orbits and been captured into permanent bound orbits through some energy dissipating mechanism rather than being born within the planet's circumplanetary disk. Irregular moons had orbits that were much wider than those of regular moons, with semi-major axes that placed them at distances from their planets of tens to hundreds of times the planetary radius, and their orbital inclinations could be anywhere from slightly inclined to nearly perpendicular or even retrograde, orbiting in the opposite direction from the planet's rotation, a retrograde orbit being the most definitive possible indicator of a captured origin, since no circumplanetary disk process could produce a moon orbiting in the reverse direction from the planet's spin. Neptune's moon Triton was the most dramatic example of an irregular captured moon in the solar system. Triton orbited Neptune in a retrograde direction with an inclination of approximately 157 degrees to Neptune's equatorial plane, the retrograde orbit being impossible to reconcile with formation from Neptune's circumplanetary disk and communicating unambiguously that Triton was a captured object. Triton was a captured dwarf planet. Its size, composition, and the fact that it was likely a Kuiper Belt object captured by Neptune during the early solar system's period of dynamical chaos being the most widely accepted explanation for how a body as large as Triton, approximately 2,707 kilometers in diameter and the seventh largest moon in the solar system, had ended up in a retrograde orbit around the outermost ice giant. The consequences of Triton's retrograde orbit for its long-term dynamical fate were dramatic. Tidal forces between Triton and Neptune were continuously reducing Triton's orbital energy, causing the orbit to slowly spiral inward, and in approximately 3.6 billion years, Triton would reach Neptune's Rauch limit, the distance within which Neptune's tidal forces would exceed Triton's self-gravity and begin pulling it apart, creating a ring system around Neptune more spectacular than Saturn's current rings from the debris of the disrupted moon. Jupiter and Saturn each had dozens of irregular moons occupying specific dynamical groupings. The Himalaya group, the Ananke group, the Karm group, and the Pasiphae group for Jupiter, each group believed to represent the collisional fragments of a larger captured body that had been broken apart by a collision after capture. The dynamically related members of each group sharing similar orbital parameters because they originated from the same parent body. Hit the like and subscribe button to see more videos like this. Leave a comment on your favorite moon in our solar system. Let's get back into the video. Volcanic moon. Io was the most volcanically active body in the solar system, not the most volcanically active moon, not the most volcanically active object of its particular composition, but the most volcanically active body in the entire solar system. Bar none, more geologically energetic than Earth, more dynamically violent than any other solid object orbiting the sun. A world whose surface was being continuously resurfaced by volcanic eruptions, whose combined output was dumping approximately 100 times more lava per year than all of Earth's volcanoes combined. Discovered in 1610 by Galileo Galilei, Io was the most volcanically active body in the solar system, with its mean radius of approximately 1,821 kilometers, making it slightly larger than Earth's moon. The source of Io's extraordinary volcanic energy was not radioactive decay, the mechanism that powered geological activity in other rocky bodies, but tidal heating, the continuous kneading of Io's interior by the gravitational forces of Jupiter and the other Galilean moons, whose orbital resonances locked Io into an elliptical orbit that prevented it from settling into the circular orbit that would have ended the tidal flexing and allowed the interior to cool. Io's orbital resonance with Europa and Ganymede, Io completed exactly 4 orbits for every 2 orbits of Europa and every single orbit of Ganymede, a 4-2.1 orbital resonance, meant that the gravitational pulls of Europa and Ganymede were continuously reinforcing Io's orbital eccentricity rather than allowing tidal forces to circularize it. The reinforcement maintaining the elliptical orbit that was the energy source for the tidal heating. The magnitude of the tidal heating was extraordinary. Estimates suggested that Io's tidal heating rate was approximately 100 trillion watts, comparable to the total energy output of 10,000 nuclear power plants operating simultaneously. And this energy was dissipated through the volcanic system as heat, erupted lava, and the continuous sulfur dioxide plumes that had been directly observed by the Voyager spacecraft in 1979 when they became the first human-made objects to image Io's active volcanoes, the discovery of active volcanism being the most surprising single scientific result of the entire Voyager program. Io's surface was covered with hundreds of volcanoes in various stages of activity, with the largest volcanic features being the Patirae, large, shallow, flat-floored calderas that marked the centers of the most productive volcanic systems. The lava flowing from these volcanoes was not the basaltic lava familiar from Earth's volcanoes, but an unusually high-temperature silicate lava estimated to exceed 1,600 degrees Celsius at its eruption temperature, hotter than any lava being produced anywhere on Earth today, and suggesting that Io's internal temperature and the composition of its magma were fundamentally different from Earth's volcanic system. Ocean world moon, Europa was the most compelling candidate for extraterrestrial life in the entire solar system. More compelling than Mars, more compelling than Titan, more compelling than any of the dozens of exoplanets in the habitable zones of nearby stars, for the specific reason that the evidence for the one ingredient most closely associated with life's origin and persistence on Earth, liquid water, was stronger for Europa than for any other known body beyond Earth itself. Europa was one of the 4 Galilean moons of Jupiter, discovered by Galileo in 1610, and its smooth ice-covered surface had puzzled astronomers for decades before the Voyager and Galileo spacecraft provided the detailed observations that established the subsurface ocean model as the most compelling explanation for the moon's specific combination of surface characteristics. The evidence for Europa's subsurface ocean came from multiple independent lines of scientific investigation. The surface's network of crossing ridges and bands that communicated the icy shell was mobile and had been fractured and refrozen repeatedly. The relatively young surface age implied by the low-impact crater density, the magnetic field measurements by the Galileo spacecraft showing an induced magnetic field that could only be explained by the presence of a conducting layer beneath the surface, and the thermal models that showed the tidal heating from Jupiter's gravitational flexing was sufficient to maintain liquid water beneath the ice regardless of the water's distance from the sun. Europa's subsurface ocean was estimated to contain approximately twice as much liquid water as all of Earth's oceans combined, a total water volume of approximately 3 billion cubic kilometers beneath an ice shell estimated to be between 10 and 30 kilometers thick, the ocean extending downward to a rocky seafloor where hydrothermal activity driven by the same tidal heating that warmed the ocean might be providing the energy and chemical gradients that could support microbial life by analogy with Earth's hydrothermal vent ecosystems. The Europa Clipper spacecraft, launched by NASA in October 2024 and scheduled to arrive at Jupiter in 2030, was designed to conduct the most comprehensive investigation of Europa ever performed, making approximately 49 close flybys of the moon at altitudes ranging from 25 to 2,700 kilometers, and using its 9 science instruments to characterize the subsurface ocean, the ice shell's thickness and composition, and the moon's potential for habitability in preparation for a potential future lander mission. Shepherd moon. Shepherd moons were small moons whose orbital positions relative to planetary ring systems produced gravitational effects that confined the ring material into narrower bands than would persist without the shepherd moon's presence. The gravitational interaction between the shepherd moon and the ring particles at the ring's edge, transferring orbital energy in a way that accelerated particles trying to move outward and decelerated particles trying to move inward, the combined effect producing a sharp outer edge to the ring that would otherwise diffuse outward as particles at the edge escaped to larger orbits. Several of the smaller moons of Saturn were found in or near Saturn's rings, keeping the rings in place, and were referred to as shepherd moons. The visual metaphor of a shepherd herding a flock of sheep being applied to the gravitational herding of ring particles by the shepherd moon's orbital proximity. Prometheus and Pandora were the most studied shepherd moon pair in the solar system. The 2 small moons orbiting on either side of Saturn's narrow F ring, whose combined shepherding effect maintained the F ring's unusually narrow and braided structure, despite the ring being located at a position where ring particles would otherwise disperse rapidly. Prometheus orbited just inside the F ring and Pandora orbited just outside it, their gravitational interactions with the ring particles at the ring's inner and outer edges respectively providing the confining forces that maintain the narrow ring structure. The gravitational interaction between Prometheus and the F ring was more complex than simple edge shepherding. Prometheus's slightly elliptical orbit brought it into close proximity with the F ring once every approximately 19 hours, and each close approach created a distinctive channel or kink in the F-ring structure as Prometheus's gravity disturbed the ring particles nearest to it, the series of channels and kinks created by successive Prometheus passages being visible in Cassini spacecraft images as a regular pattern of perturbations along the ring's length. Uranus's Epsilon ring, the outermost and brightest of Uranus's main rings, was maintained by the shepherd moons Cordelia and Ophelia, the 2 small moons discovered by the Voyager 2 spacecraft during its 1986 Uranus flyby, precisely because their existence had been predicted by the theory of shepherd moon confinement, and the discovery of the narrow epsilon ring demanded an explanation. Captured asteroid moon. Mars's two small moons, Phobos and Deimos, were the solar system's most studied examples of the captured asteroid moon type. Small, irregularly shaped objects whose compositions, appearances, and dynamical histories had long suggested that they were captured members of the asteroid belt rather than moons that had formed in place around Mars during the planet's own accretionary history. Both Mars moons were irregular in shape and were likely captured asteroids. The irregular shape directly reflecting a body too small to have been pulled into a spherical form by its own self-gravity, and the spectral similarity to carbonaceous chondrite asteroids of the C-type, suggesting a compositional origin consistent with the outer asteroid belt rather than with the rocky material from which Mars itself had formed in the inner solar system. Phobos was the larger of the two, with dimensions of approximately 27 by 22 by 18 kilometers, and it orbited Mars faster than Mars's own 24.5-hour rotation, so fast that it appeared to rise in the west and set in the east as seen from the Martian surface, the only moon in the solar system to orbit its planet faster than the planet rotated. Phobos' orbit would eventually decay, and it would crash into the surface of Mars in approximately 50 million years. The tidal deceleration of a moon orbiting faster than its planet's rotation being the orbital mechanics equivalent of the tidal acceleration that was causing Earth's moon to slowly spiral outward. The surface of Phobos was dominated by a giant impact crater named Stickney, a crater approximately 9 kilometers in diameter on a moon only 27 kilometers across, a crater so large relative to the moon's size that the impact that created it came close to shattering Phobos entirely, the system of linear grooves radiating across Phobos' surface, possibly being fractures created by the Stickney impact rather than the tidal stress fractures that an alternative hypothesis had proposed. Deimos was the smaller of the two and had a higher, slower orbit that placed it above Mars's synchronous orbit altitude, meaning that tidal forces would cause it to slowly spiral outward and eventually escape Mars's gravitational influence entirely rather than spiraling inward like Phobos. Large differentiated moon. Ganymede was the largest moon in the solar system and one of the most geologically and geophysically complex, a world larger than the planet Mercury that had undergone internal differentiation into a layered structure comparable in complexity to the terrestrial planets of the inner solar system, with an iron core, a rocky mantle, and an icy outer shell, and a magnetic field generated by convection in its liquid iron core that made it the only moon in the solar system known to generate its own magnetic field. The largest and most massive moon in the solar system, Ganymede, orbited Jupiter, with a mean radius of approximately 2,634 kilometers. Ganymede exceeded Mercury's radius of 2,440 kilometers, while having less than half Mercury's mass, the difference reflecting Ganymede's composition of approximately 50% water ice by mass compared to Mercury's dense iron-rich Triton composition. Saturn's Titan was the second largest moon in the solar system and the only moon with a dense atmosphere. A thick nitrogen atmosphere with a surface pressure approximately 1.5 times Earth's sea level pressure, beneath which a complex hydrocarbon chemistry had produced rivers, lakes, and seas of liquid methane and ethane on the surface, making Titan the only body in the solar system besides Earth with stable liquid on its surface. The Cassini spacecraft's 13 years in the Saturn system had revealed Titan as a world whose surface process mirrored Earth's water cycle in extraordinary detail. Methane evaporating from the lakes and seas, forming clouds, raining back down as methane precipitation, and flowing through river channels back into the lakes in a complete hydrological cycle using methane as the working fluid rather than water. The Dragonfly mission, a rotorcraft lander approved by NASA and targeted for a 2028 launch and 2034 arrival at Titan, would be the first mission to fly a powered aircraft on another world's surface, using Titan's dense atmosphere and low gravity to enable a drone-like vehicle to travel from landing site to landing site across the moon's surface, sampling different geological environments and searching for evidence of the prebiotic chemistry that Titan's complex organic chemistry had long suggested might be present.